In this problem, we have a uniformly charged large insulating sheet. The surface charge density sigma is given and it's positive. An electron is released from rest at a certain distance d1 from the insulating sheet. Now, what happens to the electron? At the location of the electron, there's an electric field that the surface charge density is creating. And because this is positive charge density, the electric field is pointing away from the surface, which is pointing left. And there's going to be a force on the electron due to that electric field, which will be in the opposite direction. And the force will be proportional to the electric field strength. So the force will be pointing towards the insulating sheet, which makes sense because this is an electron, negatively charged particle, and the sheet is positively charged. So there's an attractive force between the two. And here's the force vector. In part A, we're going to calculate the work done on the electron by the electric field due to the insulating sheet as the electron moves from its initial position to a point at a distance d2 from the insulating sheet. Now the electric field is doing work on the electron by applying the electric force on it, and the magnitude of the force is related to the magnitude of the electric field as shown in this formula. Force magnitude is equal to the charge of the electron times the magnitude of the electric field. Here I have everything positive because we know the direction of the force, where this is really just the magnitude of the force. Now the electric field magnitude due to a very large insulating sheet of uniform surface charge density sigma is equal to sigma divided by 2 times epsilon 0. Combining these two equations, we come up with an expression for the magnitude of the force in terms of the given variables. Now you may be asking, where does this sigma divided by 2 pi epsilon 0 is coming from? We derived it earlier, and this is a general result that you can find in any physics textbook. Next, let's calculate work. Remember, work is defined as the line integral of the force vector along the path of the particle. As the particle moves from its initial location to its final location, the force vector remains parallel to the unit displacement vector ds. So then f dot ds reduces to f ds cosine 0, and cosine 0 is just equal to 1. And here's vector ds shown in the picture. Next, we substitute the expression for force that we came up with earlier. You can see that all these variables are constant. Nothing depends on s, so we can pull everything outside of the integral. And the integral of ds along the path is simply s, the displacement of the electron from its initial position to its final position. Again, everything is positive. This is positive work. F and ds point in the same direction. They're parallel. So next, let's go ahead and plug in the numbers and calculate the numerical result. And note that displacement s is equal to d1 minus d2 in the picture. So the final answer for work is 6.56 times 10 to the power negative 21 joules. In part B, we're calculating the speed of the electron when it's at distance d2 from the insulating sheet. So basically, what is the speed of the electron after this much work has been done? Let's use the work energy theorem, in other words, work kinetic energy theorem. So this is the only work that is done on the electron. There is no other force. I mean, you may argue that there's gravitational force, but that's negligible compared to the electric force. So really the only work done on the electron, and hence the net work done on the electron is what we found in part A, and that is going to be equal to the change in kinetic energy of the electron. That's what the work energy theorem tells us. Here's the work energy theorem. Net work equals delta KE. Remember, delta means change, and whenever we have delta something, we do final value minus initial value. So work that we found in part A is going to be equal to kinetic energy final of the electron minus kinetic energy initial. The electron started from rest, so initially its velocity was 0 or its speed was 0, which makes its initial kinetic energy equal to 0. So we just get rid of this term. Substituting the definition for kinetic energy, work equals 1/2 mass of the electron times the square of its final speed. Rearranging the equation and isolating the unknown, we get V final equals square root of 2 times work divided by mass of the electron. Here's the numerical substitution and the result. Final speed of the electron is equal to 1.20 times 10⁵ meters per second.